So I want to talk about reproducibility. So um, this will be a bit of a whirlwind. This is a talk that we would love to give in other contexts. We've been able to give it 45 minutes. Here we're going to do 15. So I encourage you to sort of hang on as we fly through this and consider going back and reviewing the slides in more detail later on at your leisure. So first of all, a matter of terminology. We're going to talk about reproducibility. It's a pretty common term. There are also a lot of other terms that are used in a similar fashion to describe these concepts. And for the purposes of this talk, we don't really care. These are different in various ways, but we don't really care so much about that. So we're just going to call it reproducibility. I'm going to give one exception, however, just so you're aware. Some of these things are very specifically defined. So for example, there's a term reproducible and replicable. And historically, there have been a couple of different communities that have used these terms in opposite ways. And so just recently, there was an agreement to kind of harmonize around these things. And so the definitions that are on the slide here are the ones that will be used sort of going forward, but you may see in the past that some publishers, for example, had reproducibility badges and they had definitions which may have been different. They're being revised to reflect this change in terminology. So first, let me start out with a few thoughts on why reproducibility is important. This is a problem everywhere in modern day science, it seems, and this is an example from a project that was trying to reproduce psychology experiments, and they took, I think, 100 of them and just tried to reproduce, or social science experiments a little more generally, and they had a very hard time reproducing most of these based on what was available in the literature. And increasingly, as you may have seen, these concerns about the politicization of science and things like that really are getting out there. They're into the mainstream press quite often. And so far, computational science has fortunately been spared this kind of spotlight to a large extent, but there's no reason why we should expect that to continue. And there have been examples, even though we don't get into the spotlight, there are plenty of examples out there where there have been issues in computational studies as well. And here's just one example, a study done a few years ago looking at the nucleation behavior of water just above, looking at the behavior of water just above its nucleation temperature, and two different groups found very different physics going on, different results. And the second group after the second group published, the first group went back and looked at this and said, hey, there's obviously some difference here. How can we, check this? And they tried to reproduce it and they found that they couldn't reproduce it. And they asked for Chandler's code, and it took actually intervention by the editors at Nature to get these guys to share the code. It took about 5 years. And finally, once they had the code, what they found was a speed up and optimization had been introduced into the LAMMPS code, but it actually introduced an error. So the optimization was erroneous. Going back to our testing discussions, it obviously hadn't been tested carefully enough to evidence something like that. When they replaced it with a standard approach, which may have been slower, they got the same results as before. So, but the challenge is that this took 7 years in the intervention of the editors to actually get this to be resolved. There's another situation more recently that you may well have heard about. This is a case with a Python script that was used to identify or analyze a lot of NMR data by a lot of different people. So this is a script that was just put out there and was widely used. And it turns out that in Python's glob module, which lists file names matching a pattern, you can get different results. They're ordered differently on different platforms. And turns out that the results of the script depended on the order in which the files were processed. And so about 150 papers which had used this script all of a sudden had to scramble around to figure out if their results were actually correct. And another challenge here is this is a case where it's hard to say that a unit test would have caught this because it was different platforms that introduce these challenges. So sometimes you do testing on one platform and it isn't actually representative of another platform, and sometimes in surprising ways. So it's a real challenge. And what it comes down to fundamentally is this idea, again, that science through computing is at best as credible as the software that produces it. There are some additional incentives for paying attention to reproducibility, but we all have a lot of challenges, right? I'd love to do a better job on my software, but I need to get this paper submitted. I need to complete this task on my project. I need to do something that my employer values more, right? And so a secondary goal that we're starting to see more and more with respect to reproducibility is to change the incentives to value better software and better reproducibility, as well as the scientific results per se. And there's a variety of reasons for that. Supercomputer cycles are scarce resources. No one wants to spend their precious allocation running simulations a couple of different times to be confident of the results. And in fact, that happens more than you would think, but that isn't even a guarantee. That's really going to maybe help you identify silent errors, but it's not, if you've got something that's systematically wrong in your code, it's not going to turn that up necessarily. But there are a lot of people who need to have confidence in the results that you're producing. First of all, your project leader, your boss should have a real interest in ensuring that your results are correct. The sponsor of your work, when you're publishing a paper, the referees or reviewers of that work, and of course the readers of that work. So you really need to think about how to build the credibility for your science without spending lots of resources just repeating runs and things like that. And really, one of the best ways to do that is to build up the testing and other strategies that will give you confidence from the start that your code is doing the right thing. There are also a variety of other initiatives out there that are trying to increase the focus on reproducibility and transparency. So if anybody's done a proposal to any US government agency recently, pretty much they're requiring data management plans. That's how you're going to manage your data. Are you going to make your data available? Things like that. The FAIR principles for data access. And then there's reproducibility and transparency initiatives for publications. And I'm not going to cover these here, but increasingly conferences and other venues are sort of providing bonus points, badges, other ways of recognizing papers that have gone to the additional work to make them more reproducible. It's not perfect in most cases, but it's taking steps in that direction, and that's the goal here. The real goal is to try to create a virtuous cycle. So these reproducibility requirements will basically push people to invest in productivity and sustainability and quality improvements in their software and in their practices. And doing that, of course, enables better response to the reproducibility requirements. So we would argue that ultimately reproducibility is based to a very large extent on good software development practices, just like the things that we've been talking about this afternoon, and good experimental practices, numerical experiments to go with them. So how can you improve reproducibility? Well, there's strategies that you can use during development, during the experiments themselves, and afterwards as you're analyzing and writing things up. I'm going to go through this pretty quickly, and this is in particular where I encourage you to go back and kind of think more about some of the things that we're saying here. So first and foremost, during development, establish solid versioning practices. Basically, anytime you are running code, you want to be able to unambiguously be able to identify what's in the code and what's not in the code, right? So if you develop good versioning practices and you are always clear about how that works, you can develop version numbering schemes or identifiers based on the commit hash or other approaches to identify the software and make sure that what you're building and using is not modified from the version that's been identified in the versioning scheme that you're using, what's in the repository. This last step is not something that I see done in practice very often. And then also maintaining documentation and other artifacts in sync with the code. You're likely to forget or not make the time to go back and update things. So this is during development, keeping everything together, developing good practices so that everything is consistent and well identified. You also want to build in quality from the start. You can define and follow coding standards. You can do something like test-driven development. That's a fairly rigorous approach if you want to follow it to its, by its definition, but it's a useful thing to just really think about your testing practices and get them in place right from the start. And think about testing that gets increasingly rigorous as your code becomes more public. In other words, as you get from development to actually using it, to maybe making it available to others outside your immediate collaborators and things like that. You want to ensure that you have more and more confidence in the code. Another very useful practice is code reviews. And so you can get colleagues to review your code. This can be done on a per commit basis, although you may have a big backlog and stuff that you haven't reviewed so far. And actually code reviews of existing code can be useful to gain experience, for people to gain experience with the code base. And it also, if you can plan time to go back and revisit some of that existing code and give it the same kind of review treatment, you can improve the quality and maybe find some latent bugs. After development, testing, and more testing. So when you can add regression tests anytime you fix a bug, add a test to make sure that bug doesn't creep back in. You can always be more creative about tests. You think about the common cases and then the corner cases. You think about ways people could misuse, either intentionally or unintentionally, the modules that you're creating. Something that's very useful, especially in scientific software, are synthetic tests with synthetic data. As David mentioned, we don't necessarily know the right answers when we're doing scientific simulations, but we can often do synthetic tests that will give us confidence that the code is correct. And it's also useful to think about low-cost tests that can be always on, even if they're not so stringent, to help you detect things like silent data corruption while your code is running and things like that. It's also important to test your tests, make sure that the tests fail when they're supposed to fail, actually. So you can introduce errors into the code, and of course you have to back them back out. And you want to thoroughly verify the code. Does the code do what you intended it to do on all the relevant platforms? So you need to look with all the compilers of interest. You need to look across all the different hardware of interest and all these features, because there are many situations where there can be small, bugs in compilers, or you're abusing the standard, and the compiler might react differently. Hardware, especially when you're doing parallelism, if you're doing a GPU versus a CPU, threading will behave differently and things like that. And then to test regularly and just make sure you're keeping, even though you may not be using the code at the moment, keep the test going, because you're also changing the things that underlie your development tools, the libraries, the compilers, and things like that. You want to be able to identify when changes happen in the underlying code base, your dependencies, that impact your code. We also want to have, during your experiments, you want to have a good plan. So if you're in a team, it's very useful to designate one person to coordinate the experimental campaign. You just put them in charge. know what you need, know how in advance, how you're going to process or analyze the results. Do you have the resources necessary to carry out those analyses? That may take more supercomputer time, may take disk resources that you need to make sure you have access to, et cetera. So you need to know enough about what you're going to do so that you know roughly what to expect in terms of the results, in terms of the cost, what kind of performance you should get out of your code, and how will you convince yourself that the results you're getting are trustworthy. You can perform some pilot or test runs to build confidence and sort of work through your processes. And I already mentioned, ensure that you have the resources to go through the whole process before you embark on it. And going back to the versioning, can you reproduce the code you use for each and every experiment? And can you go back, if you had to, 3 years or 5 years later, if some other team questions result in your paper, could you go back and reproduce that version of the code? Only well-identified codes, make sure those versions of the codes have been thoroughly verified. Continue your regular testing with these versions of the code, because if you're running a month or 2 month or 6 month long numerical campaign, you're probably going to encounter changes to the underlying system. You're going to have new compiler releases, you're going to have new library releases and things like that. And you need to know when things change because of that. You can also work to capture the provenance, so understand all the agents, not just your simulation code, but you may have some scripts or other things that you're using. All the inputs, all the outputs, and all the transformations that are taking place, be rigorous in trying to capture those as the provenance of these simulations that you're doing. And it's good to have redundant approaches to make sure that you can connect everything so that if one falls down or you lose some information, that you have another way to get that back. Then after the experiment, continue as you're doing the analysis and writing the paper, continue the provenance capture activities as you're going through the data reduction and analysis process. It's good to do this, the analysis, as systematically as you can. It's good to script it, for example, rather than relying on tools that require human interaction. You can keep those scripts under version control. You can document your process and make sure you capture key intermediates in the reduction process as well. So if you capture these things machine readable form, you can go back to them. You can make them available to as part of your data management agreement and things like that. So there are some tools that can help with this, and I've got some references there, but a lot of this is really just about thinking through what you're doing and being careful and thoughtful and making sure you're using good practices all throughout code development and the numerical activities, the numerical experiments, and the final analysis and writing up the paper. So to summarize, the credibility of your science derives from the credibility of your code and the process that you follow. Scientific stakeholders are ratcheting up their expectations for reproducibility on all of us. And there are a variety of strategies that we've discussed that you can think about to try to improve your reproducibility. There's a lot of different things here. As with everything else we've talked about, I'm not trying to suggest that you need to do all these things all at once, but it's worth thinking through the way you do things and trying to identify, with a particular eye to reproducibility, what could you improve one step at a time that would have the most significant impact on the reproducibility of your work. All these things that we talked about pretty much amount to better scientific software development practices. They're the same kinds of things we've been talking about throughout this tutorial. And with that, we're at the end of the main body of this tutorial.